So let me start by trying to motivate a little bit what we are going to do now after the break. So before the break, we had this very safe little box for ourselves where we could do closed form variational inference, so we can solve all the equations analytically. This was because we chose to work with conjugate exponential family models. And then Thomas showed you that the elbow is steadily increasing and everything is very comfortable and easy to debug and nice. The problem, of course, is that you will have to stay within this fairly restrictive class of models. And there is also a problem that you would have to do the analytic pencil pushing that would lead you to the update rules. Now, after the break, we are going to, or after the lunch, we are going to go outside this class of easy models and start looking at more expressive stuff. So this is a new setup. We are going to use new techniques to optimize the elbow. But we wanted to show you this more old schoolish closed form solution thing that we had before lunch anyway. And the reason for that is that we hope that that has given you some insights into what variational base is trying to do. You've seen the behavior of the models in simple models where we can actually understand what is going on. And that was supposed then to give you a starting point to better understand also what happens now after the break. Okay, so now I'm going to show you a small example with a neural network and how that can be put into a probabilistic AI setting. So what we're doing here is just to sample some data like this. The data is following a sine curve with some steadily increase added to it, so there is a linear trend also, and then there is a good portion of Gaussian noise on top. So this is the system that has been used to develop the data. We have removed a little bit here in the middle, and also there is no data at the end. And what we're going to do is to try to learn a model, see how it behaves, how it kind of fills the gaps in the data, and try to understand if that is a good or a bad behavior. So of course, if we are going to fit a standard machine learning model, then any way of completing the data here, so any way of filling in the gap here would be okay, because we don't have any data to tell us what is the better approach. So say a flat line here or something like that would be what you would expect, of course. And then out here, when we extrapolate outside the data distribution, also here, something like that would be okay. So any kind of line, basically. But we don't really know what this line should be. And that is, I guess, the point. So we are training a neural network, doing that with PyTorch. We have simple input of x, output of y, 250 hidden nodes in between, hyperbolic tangent as a nonlinearity, and keep on going. And these are the results. Oh, so we got a continuous line, but not necessarily the one we expected. But then, as I said, any model here is kind of okay-ish. We don't know what's happening because there is no data to support us in choosing one model over the other. And then the neural network here, based on the starting point, of course, of the gradient descent, was just like ending up in this way. Okay, so far so good. Now let's basify the whole thing. And what we are going to do now is to say that, okay, our weights in the neural network, they were selected to be fixed numbers for the neural network, but now I'm going to rather make them random variables. So each weight in my model now is a random variable. And this is helpful for me because then I can sample from the posterior of the weights afterwards and expose model uncertainty, right? So this would be the idea. I'm learning posterior distributions of the weights, sampling a number of weights and seeing what that means for my model. Then also I am here changing the output a little bit. So now I'm assuming that the output is the mean of a Gaussian, and then I'm expecting some noise around that. So this noise here is partly used to explain why this line is not going to go through all my data points. So I'm kind of accepting that this is not possible. Okay, so what happens now is that I'm using here something called Pyro. You will see that more in detail later, so I'm not going to tell you how it works. Simply just say that this is an add-on, or an add-on basically to PyTorch, and integrated with PyTorch, so I can use PyTorch nonlinearities, for instance, still in my model description, as I do here. So that is okay. And then I have random variables like up here as well. So I'm kind of extending PyTorch with these random elements, or stochastic elements. Yes. So that's how this works. And now I'm optimizing here the elbow. So it's kind of the same thing, but now I'm doing this by gradient descent or gradient ascent. So what's happening here now is that I have a non-monotonic behavior of the elbow as we go over the epochs. So you can see it's not as quietly improving all the time as it was before lunch. Yeah, plotting. So this is the output from the Bayesian neural network. So what we have now is a couple of red lines here. Those are samples from the posterior distribution of the weights leading to instantiations of neural networks, and then they have been evaluated, generating these red lines. So we can see that over here, for instance, where we have lots of data, they are more or less agreeing. Over here, we had this hole in the data. We have a model uncertainty that is clearly exposed by these lines being not covering very much over the area, but still they are more spread out and showing that we are uncertain about the model in this area of the x-axis. Okay? And then the yellow part here is just the two standard deviations plus minus for the posterior predicted distribution, so showing something about what kind of a certainty I would have to this. All of this now because I was casting my neural network weights as random variables instead of as parameters that would be optimized with a point instead of this distribution that we have now. We do the elbow or the ProbAI. Yeah. So I'm not predicting the variance of y in here. And that's why we have this, you are my new favorite, optional task. So good segue. You, specifically you, after today can sit here and play around with the code and try to learn that. So I have actually been a little bit of a silly guy also, because we've hard-coded the variance to be 1, even if it was 3. So that's a problem. And then we can try to learn it somehow. And there are different suggestions on how to do it here. Okay, so that was kind of the trying to show you that we can use elbow for stuff that is not simple linear regression. And that's what we will lead up to now with some math. Okay, so I'll start with stochastic gradient descent. And we all know what that means, and I'm still going to talk about it. And the reason why is that we are going to optimize the elbow using gradient ascent or descent, depending on whether we multiply elbow by -1 or not. And I just want you to have the same type of notation as I have here in the slides. So we know that when we want to optimize a function, then we can do that iteratively by starting from somewhere and then making small movements in the direction of the gradient all the time until we have converged. And then we will have a local optimum of that, something that we try to optimize. So if f here is our objective function, then we need a gradient of f. We evaluate it, move a little bit in the direction of the gradient, multiply with the learning rate, keep going. This works if f is nice and rho is small. So that's kind of the starting point. But that's not enough for us. And there are reason for that, we don't really know. The reason for that is that we don't really know what the gradient of the elbow is going to be. It is hard to calculate this in for at least two different reasons. First one, elbow is considering all the data to be calculated correctly. Sometimes we will have more data than we would like to put in memory at one time. Maybe we'll have to do batching then, and therefore we are evaluating the elbow of a random subset of the data instead of the whole thing. So that is not then the elbow, it's a subset of data. So we need to think about that. Secondly, even though we have a small data set, it might be hard to calculate the elbow exactly anyway. So we will need to have something that doesn't work or doesn't require us to have the exact gradient for the elbow. And that's why we talk about stochastic gradient descent now, which is more or less the same thing, but now we have replaced the gradient of our objective function with an unbiased estimate instead. So we don't really have a gradient of f here anymore. We have now g, which is a random variable that has the expected value equal to the gradient that we were searching for, and has a variance that is finite. So we need this random variable g now, correcting expectation, limited invariance, and then we can actually replace our use of the gradient of f here with this g instead. And this works if we change the learning rate to now be a Robbins-Monroe sequence, which means that it is not a constant, it's a number of small numbers. These numbers are so small that they converge when they are summed squared, but they diverge when they are summed non-squared. So something like 1 over t or whatever would be a possible Robbins-Monroe sequence. So we are going to then look for this g function that can be the unbiased estimator for the gradient of the elbow, and then if we find that, we're good. Okay, so black box variational inference. We want to somehow optimize elbow by gradient methods, and the motivation for this is that then we don't have to restrict ourselves to model classes where we can do the calculations by hand as we did before lunch. We will rather than kind of outsource the task of optimizing elbow to a gradient-based method thing, so like PyTorch, and then just make sure that the loss function is actually the minus elbow, and then optimize that way. So that should be possible as long as we can calculate this gradient of elbow. So this is then the algorithm that we are looking for. Start somewhere with parameters lambda, have some sequence of learning rates, and just move along until we find parameters that we like. We are still optimizing these lambdas, so that means the indexing into the set of possible approximation candidates. You remember we have this set of Q, and then we have this lambda thing to index into that. We are still then therefore doing continuous optimization, trying to find the lambda vector that fits our purpose best. And by fitting our purpose, we mean optimizing the elbow. So this is all good and nice as long as we can calculate this thing here. And now we will see how we can do that without making new and restrictive assumptions on the modeling class P or the approximation class Q. Okay, so we need this elbow gradient, and that is this thing here. And the problem now is, what do we do with this gradient in relationship to the expectation operator? So typically, when you are faced with an expectation operator in ProbAI world, what you will do is basically just to sample your way through it. So when I'm going to make an expectation over theta here coming from the distribution Q, I'll just sample a number of thetas, evaluate the function that I'm taking the expectation over, and what I'm getting out is an unbiased estimate for that expectation. So this is exactly the words we need, right? It's an unbiased estimate of what we want to calculate. So far so good. Problem now is that this gradient here is with respect to the distribution we are sampling from. So one way to kind of think about fixing that would be to sample from some lambdas, get an unbiased estimator for this for that lambda, and then move a little bit of and then do it again. So move a little bit in lambda space and then divide by that and kind of let this difference go to 0 and stuff. But the variance of that is obviously going to be really, really huge, and then this is falling apart. So what we will rather do is to try to find a way to be able to defend mathematically moving this operator here, the gradient, inside the expectation. And that can be done. So there are some properties of gradients and distribution functions that we are not going to bother you with too much, I guess, but just say that using these three, the product rule, the log rule, and here something called the score function property, then we can actually then push this gradient operator inside the expectation term. So then this guy here suddenly is going here. So these two gradients are the same. And we do have a heart, so we didn't want to bother you with actual pencil pushing details for how that works. It's not that hard, but it's kind of tricky, so we just didn't bother. But this is then the result. We can calculate the gradient of the elbow in this way. And now we have the expectation outside here, so that means we can sample our way to get an unbiased estimate of this expectation and therefore of the gradient of the elbow, and then stochastic gradient descent will work. So let's see how that works. This is the beast we are confronted with. First, notice we are still talking about the joint over theta and d, not the posterior of theta given d. So this is a quantity that we can always calculate. Next, we can do mean field on this part here, but you don't have to. Then when it comes to this guy, this is a new quantity. It's called the score function. It needs to be calculated. So we are writing out what is the structure of our log Q, and then we are finding the gradients. You will see this in the notebook soon. And then finally, the expectation is simply calculated by sampling, or approximated by sampling, I should say. So this is then the summary. Just like, go ahead. This needs to be calculated by hand, then sample from our current configuration of lambdas to give us theta j samples, and then take it from there. The number of samples here is so that the more samples you have, the better the approximation to the elbow gradient is going to be, of course. Nevertheless, people typically choose this to be, say, not too big, if that's a good way of putting it. You'll see what that means in a couple of slides. So we don't really need to have this thing here perfectly calibrated. We just need it to be ballparkish, moving us in the right direction. Remember that the requirement is the estimator needs to have finite variance, and that's going to work anyway. Okay, so let's see how this is going to play out. Here we have our good old example with the true posterior blue curves, current estimate of the approximation, green curves, so the contours are given like this. Of course, we would now like to push this green guy over here. So what we do is that we are in need of this property here, or this object here. So what we do is to sample. And the samples that we have made here are these black dots. So let's look at this guy. That is one of the theta j's that we have sampled in this sum. So first thing to look at here is the red arrow, and that's this quantity, the score function. That is asking in which direction should I move Q to make this sample more probable. So basically what it's doing is to suggest that we should take the whole approximation, the whole Q, and push it towards that data point, right? So that's this quantity here. So this means we have a vector here that points away from the mode of the approximation that we have. Next, the black vector, which is here, is now the red one multiplied by this weight. So this log fraction here is the joint probability of the model and the data divided by the probability for that sample under the current Q. Notice now that this one here is typically larger than this one. One thing is that we sample theta I from Q and not from P, so when they are not overlapping, this is probably then going to be more well calibrated for theta I than that one. And also, P is a joint over model and data. So this one is, of course, then smaller due to the data part. So in all, this fraction is less than 1 in very, very, very obviously almost all the time. And then the log of that is going, therefore, to be a negative number, meaning that we switch direction of this red vector to go through the middle of the Q distribution instead of directly away from it. So that's what happens here. And the length of the vector is given by this numerical size of this, meaning that if we have something that has made this one really small compared to that one, the vector is longer. So things that are far away from the true distribution is going to be weighted more, have longer vector than things that are close. So compare this guy to that guy, for instance, right? And then we just average out, and this gives us this green vector now, which is the end result from these 5 samples. The distribution is going to be moved a little bit in that direction, depending on the learning rate. Okay? All this makes sense? The blue one here is the true. This is P of theta given D.
So those 5 data points
The 5 data points are sampled to make this expectation here kind of go away. So we need to sample from the Q distribution, yes. So we are kind of filling up here, this formula here, with theta j's coming from Q. So what I was trying to show you was that this part here is going to be pointing away from Q, and then this thing here is going to be negative. So all the vectors here are pointing through the mode of Q and then somewhere, and then the weighting is happening, and then that gives us the update that we are doing this time. And then we move a little bit, sample again, get a new update. The reason why what is closer to...
The idea is that we're moving Q closer to P. The reason it's moving is because of that weighting.
Yes. Yes. So if you have like one example that, or sample that's here and one that's here, so that the Q values are the same, then the guy that is closer to P is going to point in this direction, and it's going to be less in numerical value than the other one that's further away from P. So that's the one far away from P is going to cancel the other one out and push in the right direction. But this is highly volatile, and the randomness is big, so high variance in these operations. Maybe? Yeah? So each of these data points is kind of saying that, please come to me. I want to have you closer to me. That's this red part of the gradient, right? And then we are weighing that, and then through this that we just discussed, the average is going to be on the average will on average point in the right direction. So this green arrow is a sample that is on expectation correct, but here not so good. Again, you're giving me a good segue to the next slide. Have you seen my slide like earlier? No? So here are several repetitions of choosing 5 random samples and seeing what the result is. And then that differs. So here we have a direction there, that is the average. Here we are moving in this direction, here we are moving directly away, and here we are doing a good job by moving in the direction that we want. But the problem here is that we are all the time like reliant on having a little bit of luck. So 5 samples here seems to be not enough. And what we're doing here now is to increase the number of samples. So here we are estimating this expectation with 3 samples, and luckily enough there was a good set of samples here, so we move in the right direction. 5 is not so good, and then 10 and 25. And for 25 we are moving in the right direction, and this is kind of stable. But for 3, 5, and 10 there is a bit of variance here that makes this unstable. And that's basically what you are going to have to play with now when we get to the notebook. I'll just show you this movie to see the behavior. So you can see that it's now like dancing around a bit, this green approximation that we have. It's not, the previous one we had was like steadily moving in the right direction all the time and had a plan with its behavior. Whereas this guy is more moving, right? So sometimes the variance goes up, sometimes it goes down. But then eventually it's kind of stabilizing. But not to a complete stop, so it keeps dancing there and then waiting for the learning rates to go sufficiently down to stabilize. Okay, so now we are going to ask you guys to try to have a look at this. We have prepared a notebook that is doing almost all of it. But what we want you to do is to finalize this. So I'll show you the notebook. Yeah, I have just now hidden all the internal cells of stuff that you don't really need to look at. So the task is, here we have written up the gradient of the elbow, how it's calculated, given you the model. It is again our good friend, the linear regression thing. Prior likelihood part, the assumption of the Q. So it is a mean field assumption, and they are supposed to be Gaussians, both of them. So we need to then calculate the score function and the weights. So that will be this part, the red vector in the slide, and then that part, right? The weighing you have been given for free in the code, and the gradient is what you are supposed to calculate. So that is, we need the partial derivative of the log of Q with respect to mean mu and standard deviation sigma. And the standard deviation part has also been given to you, so you only basically need to calculate this thing here and put it into the code. And you do that in the code in this function called the score function gradient, which is then supposed to give you the gradient contribution from one sample. So here we are doing mean equals 0, and you need to come up with the correct formula instead, and then use that. For the standard deviation, it is given like this, and that is already implemented here. So you see that we are using a data class that we call parameters that has 2 slots, mean and standard deviation. The mean guy that you are filling in now is expecting a 2-dimensional NumPy array, where we have theta naught 0's mean and then theta 1's mean as the 2 entries in that NumPy array. And then when this gradient has been defined, you can run this little snippet here, which then kind of packs this function into a dictionary and sends that dictionary to something we call compute gradients. And that is a support code that is up here. And what this does is basically just to sample data points, evaluate using your function, aggregating, moving, sampling again, moving, so doing all these steps. So this is your task now. How much time, Thomas? So I think this assignment here kind of looks harder than it is supposed to be, and it is. So what we are looking for here is the gradient, right? So we need the gradient of log Q. And log Q is given here, so it's a Gaussian. And now we are going to do the gradient with respect to mu. So that basically means just like partial derivative of the whole thing here. This one goes away, this one goes away. Now we need to do the derivative of this with respect to mu. And that's all. So that is like this. And then I need to fill that into here. So now I have two dimensions. I have the W0, the offset, and the W1, the incline. So that means I have to take care of this twice, kind of, or for both dimensions. So that's why we have a two-dimensional area here. Similarly, the derivative with respect to sigma is what we had implemented below there. So this thing here is implemented here for the standard deviation. And then the reason why this is hard, I guess, is because there is so much packaging going on. So the code base here is supposed to be a little bit general because we are later using it again for something else. And therefore, lots of what's happening here is abstracted away. But what comes into this specific function that you have been playing with was the current distribution that we had, the prior, the observation noise, and the data. And then we are basically generating the gradient back, which is evaluated there, right? So this is then how it works. Sample once, calculate the weights. We had done that for you, and then fill in the gradient. So all of this is then fairly straightforward. So when we run this, there will be a number of warnings. And these warnings, they are triggered when the update step tries to make the standard deviation negative. So this is just like because we didn't parameterize using log sigma, for instance, instead of sigma, something like that. And therefore, there is a number of warnings being thrown, but no hard fault because of that, because we just ignore those update steps. And then you can see that we are basically moving in the direction that we want, coming sooner or later towards where we should be. So hopefully you are able to do this, and if not, then I'm sorry for like being a little bit unfair on you with all this Python packaging around, making it harder to understand than it really should have been. Okay, was this like okay? Did you get at least understood what I was doing when I did it now? If you were unable to do it before, I hope that you could then appreciate what we wanted now. Okay. Question?
Could you repeat what the warnings are?
Yes, the warnings are triggered when the update here is trying to send you to a position where the sigma is too small. So it's just because we didn't bother to do parameterization. So we could have been parameterized with log sigma or something like that, so we didn't have a range, so we could do more clever stuff. That didn't happen here. We just wanted it to be as simple as possible. So what we have now is, before lunch, we had a way of learning or maximizing elbow that was very efficient for a small class of models. And then after lunch, we have looked at a not so efficient way of updating elbow that works for almost any kind of model. So what we expect from our model here is basically that we need to be able to calculate these things. So we need to be able to calculate this gradient here. We need to be able to sample from Q, and basically that's it. If that works, we can do the updating of the elbow. So very few requirements, more or less general purpose, but then also the behavior is not as robust. And what we will do now is to look at a little bit of a sweet spot in between, where we are making some assumptions about Q that are additional to what we've seen before, and that will help us a lot. Okay, so we want to then attack this gradient again using more mathematical assumptions. And the assumption that we will come up with is the reparameterization assumption. So we have this, we start off with that we have this distribution here, Q for theta. It is parameterized by lambda. So we can then sample values from this distribution for when we want to have samples from theta, right? Or for theta. What if we didn't have to do it that way? We could do it maybe a different way. This is what we're going to do now. And the reparameterization assumption says that we are supposed to be able to generate samples from Q here in a different way. The way is first sample from a base distribution that is not depending on lambda at all, and then use a deterministic function to translate from these epsilon samples that came from the base distribution and into theta samples that come from the Q distribution. So if this works, then theta is reparameterizable, and that is a good thing. So it sounds a little bit abstract, but you have, I guess, seen this a lot, specifically working with the Gaussian. So here I'm having a Gaussian distribution for theta. Q is now the Gaussian with some mean and some variance. So my lambda here is mu and sigma. Now I can reparameterize Q by using that a Gaussian with mean and standard deviation like that can be sampled from using a standard Gaussian, no parameters going in here, and then a deterministic translation from that standard Gaussian into the Gaussian that is parameterized by these two parameters, mu and sigma. So this is something you've seen before, I guess. And this is then the concrete example of a reparameterizable distribution. So this is now the type of distributions that we will work with in an attempt to come up with a better way of calculating these gradients that is more robust. Okay, so this makes sense for you? You can understand what this reparameterization means? Good. So let's assume that it actually is possible. Q can be reparameterized. Let's see what then happens. So the gradient here was difficult because we couldn't take the gradient through the sampling distribution, right? So that was what we were struggling with. Let's utilize that this can be changed now into samples of epsilon instead. So that's what happens here. We are changing the distribution that we focus on to be the one with epsilon, and then we are changing thetas here to be this function of epsilon so that we have kind of not changed anything during our calculations here. And now, of course, this expectation is not related to lambda, so now we can switch the ordering of these two operations. We can take the gradient inside the expectation operator without making any problems for ourselves, because this one is unrelated to lambda. So last step would then be to calculate this stuff here. And that is just a chain rule. So this whole thing with gradient with respect to lambda would be the whole thing with theta, and then the gradient of our translation function after. So this is straightforward chain rule operation, right? So now we have, given that we can reparameterize our Q distribution, a new way of calculating the gradient of the elbow. So this is then how it works. If you're used to computational graphs from deep learning frameworks, then this would be the computational graph of our original way of representing the problem, where we have the deterministic nodes down here, but we have a stochastic node here, leading into the elbow. And now the backdrop operation is not going to go through that stochastic node, so we have a problem. This is the reparameterized form, where we have taken the stochasticity out of that node and put it down here on the side. And now the backprop is going through theta without any issue, and we get back to where we want to be. We can calculate the gradient of the elbow with respect to the parameterization of the Q distribution that we have here. So this is how it's helpful to do this reparameterization trick. Okay, the actual calculation is, of course, through Monte Carlo estimation, meaning we sample our way through this expectation operator. Here I have m samples. I have here the sampling scheme. So you sample from our base distribution, we translate into theta values, and then we just calculate stuff here. Okay? So it looks like fairly easy to do these calculations here. So this is more to the point, I would say. These gradients work better than the score function-based ones. And if we investigate what we are actually calculating here, we can kind of see why. So if you remember previously, we had this, these small gradient vectors, the red ones, they were pointing only based on the Q distribution. Now here, our gradients will be influenced by the model and also the approximation. But the important part is the gradient with respect to the model. So moving towards where we want to go is part of the gradient calculation. So then, of course, this is going to be better behaved. So we use the model's gradient, the blue part there. That is a nice thing. The requirement is that the Q distribution must be reparameterizable, and we are also calculating this gradient here. Previously, we did that gradient with respect to lambda. Now it's with respect to theta. And as always, we need to be calculating this log joint distribution as well. This plot here is supposed to show you the difference between the two. There's the pointy thing. So here we have the score function gradient, and then these samples here kind of add up to give us a decently averaged out vector. So we're moving towards the mode of the other one at least. And it's kind of high variance between the vectors that come out of each sample, as you can see. Here we have the reparameterization plot. And the cool thing here is that each and every guy here has a gradient vector pointing towards where we want to go, right? So you can see that the variation between each sample here is really small. And the only reason for making lots of these guys and averaging them out would be to be good at guessing what length to have on the vectors. They are pointing more or less in the same direction anyway. So for the reparameterization gradient here, we can typically have very few samples. Often only one is used in practice. Whereas over here, as you would have seen already, we need more. So yeah, this is why then reparameterization gradients are used when we can. So if the distribution is reparameterizable, then that is a good thing. Quick comparison before you get to try to play with this. So score function gradients, they pay these guys, the gradient vectors there point towards the mode of Q, so not informed by P, which is what we're trying to optimize. But the P is then used for averaging out these vectors and therefore indirectly influencing the average vector and therefore making us move in the right direction, but with high variance. The requirements for that guy, for the score function is fairly limited. We need to have something that is differentiable here. And we need to be able to evaluate the log p of the data and model together, as always. And this one, you remember we choose the family there ourselves. So making sure that this is differentiable with respect to lambda should not be a big problem, and therefore this score function gradient is very often useful or usable. The reparameterization is harder on the requirements. Q must be reparameterizable, which is the big problem, and then we need to have a log Q differentiable this time with respect to theta. And we also need to have the model data joint to be differentiable with respect to theta. But if all that works, then reparameterization is better. If not, then score function is the go-to solution. Okay, so now you are asked again to play around with this black box variational inference thing that we have looked at already. For the reparameterization, we have actually implemented everything. So the code that is there is supposed to work. What we wanted you to do was to play around with the settings of the algorithm. So number of samples per iter here is the number of samples that we average over, the m in the slides. See what happens if you choose 1, for instance. The learning rate, can you live with a larger learning rate maybe for this type of problem than we could for the previous one, when we did not reparameterize? And the number of iterations that is needed, is it stable enough to do this quickly or not? So just try to get a feel for this. And yes, this last part here is going to plot the elbow for you, so you can see if your model has somehow converged. If you want to compare with the score function based one, then it might be good to have the solution for that. So I'm going to leave that thing on the screen, so you can quickly put that into your notebook if you haven't been able to solve the solution yourself. Like here, this is the one that you need. Okay, I just very quickly wanted to show you the results of the reparameterization tricks behavior. So for this assignment, it wasn't really that hard. All you needed to do was to play around with the settings here. What I've done now is to choose m equals 1, so no samples per iter equals 1 here. And then just wanted to see the behavior of that. So here we can see the development of the elbow. The reparameterization is the orange one, and the score function-based gradient is the blue line. And here we are, on the right-hand side here, we are zooming in on the last 10% of the search. And we can see here that the reparameterization is stable. It's converging to a better elbow value than the score function-based approach as well. So this is kind of then reinforcing our expectations about the reparameterization being very useful as a trick. Whenever it can be used, we should use it. Okay, and now Thomas is going to talk to you about Pyro, which is the language that you could use for making these models efficient.
Yes, so now Helge has taken you through all the gory theoretical details, and now we are going to switch to a more practical perspective, and that sort of holds mostly for out of the day. So we are going to continue until 4 o'clock. There will be a couple of exercises included, so there would also be an opportunity to go out for a bio break if that's needed. We have already, so we saw from Andrew Johnson, he gave a short introduction to Stan the other day, and Helge has also showed a bit on Pyro when we had the Bayesian neural networks. And what we are going to spend a bit of time on now is to get sort of slightly better overview of Pyro and what you can do within Pyro, specifying models and doing inference and learning in these types of models. So Pyro was originally developed by Uber, but I think back in 2019 or so, the development of Pyro was taken care of by handed out to a community. So that's mostly been the development there are mostly driven by the community directly. It is based on PyTorch, so if you are familiar with PyTorch, most of the constructs in Pyro should be pretty familiar to you, but still there are some new ones that we are going to take a look at here. And if you're not familiar with PyTorch, then you shouldn't worry too much. We are going to take it relatively slowly to go into it. So Pyro is a general probabilistic programming language where you can use for specifying models, and I mentioned it's integrated with PyTorch. So the same constructs that you have in PyTorch can also directly be used within Pyro. So if you're, for instance, using Pyro or PyTorch for specifying neural network models, then the same type of models can also be integrated within your Bayesian setting in your probabilistic programs and such, specified within Pyro. There are a range of different inference and learning methods available. There are the Hamiltonian Monte Carlo that we heard about yesterday, but more importantly from our perspective is that there's support for variational inference. There's also different types of variational inference, including both the score function-based method that we talked about and also the reparameterization-based method. And this is what we'll take a look at now, and for that we have a notebook called PPL Intro that you can find on the GitHub page, and we're just going to install it. The packages needed. So I'll spend give a brief introduction to the basic constructs and how to do modeling here, and then after doing that, we're going to take a closer look at how to actually specify your variational distributions and learning them automatically. So Pyros allows you to specify models over a wide range of probability distributions. There are natural support for normal distributions, beta distributions, gamma distributions, what have you. So if you want to specify a normal distribution, for instance, we are including up here Pyro distributions as dist, and now we specify a normal distribution with mean 0 and variance 1, and this is sort of the object that we get here. From the distributions we can sample, and this is just using the sample construct, normal.sample in this case here, and out comes a scalar embedded within a tensor object. So tensors are in this case here, we generally considered a multidimensional array. And since we are sampling from a standard normal distribution, we're only giving one scalar, and again, it's embedded within a tensor object like this. We could also specify that we want a tensor, a three-dimensional tensor, with these dimensions that we have here, or sizes that we have here, and then you have a tensor of 3 dimensions, and these are sort of the numbers that we get from this. Good to know, if you want to find the shape of a tensor, then you use shape. So here we make a sample, we have a tensor, and then we get this, the shape of that tensor by simply sampling.shape. With your samples that you've generated, you can do various operations. You can, for instance, calculate log likelihoods if you're interested in model fit or doing other types of optimization. So we are looking at a normal distribution. We are taking the log prop of the sample, and then we get the value here. In this case here, we had our sample was a 3-dimensional tensor, and these are then the log probabilities that we get, and then we can add everything up using torch sum. So the sum operation within PyTorch summing over the elements in our tensor here. We can define multiple distributions within an object. So here we have a normal distribution that has the same, or 3 normal distributions with means 1, 2, and 3, and with a standard deviation of 1. And then we get a normal distribution here, from which we can sample, and we then get 3 independent samples from this distribution that we have here, again, embedded within a tensor. And we calculate the log probability of that sample, and here we get a log for each of the elements within that tensor. They are considered independent of each other, and that's why we then get independent log probabilities. So these are sort of the tensor object and distributions are the fundamental constructs for specifying the models. Models in Pyro are considered stochastic functions that are defined over random variables corresponding to samples, which are primitive stochastic functions. So if we are, for instance, making here we have a small running example involving trying to estimate the temperature in a room based on sensor measurements. We don't have a sensor yet, so this here is just a model of a temperature. So we define a function model that contains the Pyro sample statement, and here, when you see Pyro sample within a model of this type here, you should think of it as a random variable. So it's given a name, in this here case here temp, and it's given a distribution, a normal distribution with mean 15 and variance 2. And when we invoke the model here, it returns the sample temperature. And if we invoke it twice, then we get two different values here because, again, it's a stochastic function. We draw a random sample each time the function is invoked. Pyro has some convenient functionality also for visualizing the models. So random model gives you something like this. Again, not very fancy in this case here because we have a very simple model with just one variable, and that's it. If we make it slightly more complex by saying that we don't know what the temperature is exactly, we have a sensor for actually measuring that, and there may also be some noise associated with our sensor, then we can make a new model class that we have down here. So we are first defining our temperature. This is what we have here, just as before. And then we have a sensor, which is a random variable named sensor. It has a normal distribution where the mean is defined as is equal to the actual temperature in the room. And then there's some noise associated with the sensor. In this case here, it has a variance of 1. This model class here defines this model here defines a joint distribution over both the sensor and the temperature, and we get sort of samples from that joint distribution by returning the tuple temp and sensor, the two variables that we sample when we define the model. And our new model looks like this, where we also have the specification of the distributions out here. And we can sample from the model. And you get what you would expect, two values corresponding to each of the two variables. Making models is fine. What we want to do it for is inference and learning. And this is what we are going to look at, or take a brief look at now. So we have here a wrapper function that we have made to make it slightly more convenient for showing you some of the examples underneath. SVI, so it's for stochastic variational inference. I will just say a few things about it and then go into more detail later. So when we call this function here, we are going to do variational inference, and actually stochastic variational inference. The function takes the model that you have here, any observations that you might have about your model that you want to, that you've specified. In our case, we are going to put in observations on the sensor node a bit later, but that will come just after this, when we've shown this function here. Then we have the guide up here, and a guide in Pyro corresponds to a variational distribution, or rather a family of variational distributions. So we can specify it as none up here, meaning that we don't really provide a family of distributions. We leave it up to Pyro to define what is a suitable class. And there are numerous default variational distributions to choose from. And what we have done here is just to say that we assume, say that everything, all our variational distributions should be normal distributions. That's just for convenience. After this, I've shown you these examples from Pyro. I'm going to show you how to specify your own variational distributions. So moving away from the default settings that we have here. And then we are doing inference in our model with respect to the variational distribution we've decided to use, stochastic gradient descent with a given learning rate and momentum. And then we are sort of looking at the elbow for doing the optimization. And then we are reporting the progress in terms of the elbow. So if we are going to play around with that, we need some observations. So here we are just looking at one temperature variable, one sensor variable, and then we assume that we have one observation of the sensor. In this case here, we assume that we have observed the temperature to be 18. We provide this as argument for our function here, and we can then include that into our model using the keyword ops down here. So ops equals our observation given as argument here, and then we are indexing in sensor. And when we do that, we have a model, we are rendering it like this. So by convention, all observed variables here are grayed out. So we have this one here observed. We want to do inference now, calculating the posterior distribution over the temperature. Given our observation, that's just Bayes' rule that's coming into play again. So, and what we do with that, we're not calculating it exactly here. We are using our stochastic variational inference. So this is what's happening over here. I'm calling my wrapper functions SVI with the model that I defined at the top, ops, which is the dictionary with the single sensor observation that I have, and then I'm going to do a bit of plotting and printing out the results afterwards. And this is what I get out of it. I can see sort of I'm increasing my elbow here. We have a plot of the evolution of the elbow over 500 iterations. And I print out here the posterior distribution of the temperature given the sensor. And maybe a small note on that. When you want to access the variational parameters that have been calculated in Pyro, you can access it via the parameter store in Pyro, so Pyro param, and then you have the name of the parameter of interest, and then you can then extract it in that way. Good. If we have a bunch of observations, so now we not just have one observation of our sensor, we have multiple observations in independent. So let's say that you are measuring temperatures in different rooms that are independent of each other, different buildings, in the same building. So we have a model that looks something like this. What we have done here is to wrap our, say that we have 10 observations in total. So we want to make a replicate of our model 10 times. So just as we've seen before that we can use plate notation for doing that in terms of when we are making the graphical specification, we can do the same thing using Pyro by simply having Pyro plate. So with Pyro plate, then we have our the name of the plate and the number of instances that this plate here should iterate over. So you can think of this here as a for loop. Actually, you could also be using a for loop here, but by using this plate construct, you are explicitly telling Pyro that the variables within the plate here are independent of each other. So, and if Pyro is told that these are independent of each other, then the inference can be parallelized. So it's much faster than doing a for loop here, but in principle, you could set a full for loop out and that would give you the same result. We can now run inference with our observations in this new model here containing 10 values, and we can get the names of, and we can see the results. First, we get the names of the parameters that are being learned from the parameter store. And that's just, the general names are just these two guys here. Remember that we are using the default variational distribution provided by Pyro, so these are just default names that are being set. And then we can access them and print out the results that we get. And these are the distributions, our posterior distributions that we end up with, conditioned on the observations that we have. This was just to illustrate some of the functionality. It's not that interesting because we are just providing data and we are not really doing learning. So if we want to do learning, we could maybe ask, what if we don't know what the mean temperature in the rooms is? So we could introduce a parameter mu of t here, that would be the mean temperature, for which we could say that the temperature in each of the room is then would be dependent on that. So here we are setting the scene for maximum likelihood approach, where we are have defined our model like this, where this here is an unknown parameter to be estimated. So we are looking for the parameter mu of t that maximizes the log likelihood of our sensor observations down here, given mu. And this is sort of the way we could calculate that. For defining these unknown parameters that should be optimized by Pyro, we use the Pyro param construct here. So if you want to specify in your model that we need to have an unknown temperature, what you can do is to introduce mean temp here, which is defined as a Pyro parameter, given a particular name, and initialized to a default value, in this case here 15. And then we let the temperature variable that we have in here be defined in terms of the mean temperature up here. So the mean value down here corresponds to the mean temperature parameter that we've defined outside our plate. So in terms of model, then we have something like this. Our model from before, but the mean temperature parameter is now defined outside the model. It's defined as a parameter and not as a variable, as you can see the difference that we have here. We can run inference here, and these are the results that we get. Again, we can access our parameters using the Pyro parameter store and getting the mean temperature, and the parameter value that we get for the parameter that we have named mean temp is then 19 point something down here. And just for reference, I'm storing that in this variable here because I want to compare it in just a second. Because I could also, as alternative to maximum likelihood learning, I could also put this within a Bayesian setting. So let's say that I define my, my mu of t is an unknown uncertain quantity. I have a prior distribution over it, so my model looks like this. And my inference problem is as I've formulated up here, so it's just an application of Bayes' rule, but where I'm marginalizing out, in this case here, up here, in the numerator and the denominator, having marginalized out the temperature variables. So the way to do that is simply, again, here I have my mean temperature defined as a random variable called mean temp, and given a prior distribution that's normal with mean 15 and variance 2. Everything else is identical to what we had before. We have the same observations up here, 10 observations in total. Our model now looks like this, so we can also see mean temperature here is now visualized as a proper variable. We can run inference on it by calculating SVI again and print out the values. So what we get here now is, if we look into the random variable that we are interested in, and we print out and get its mean and standard deviation, the scale in this case here, then we get these values here. So in this case here, you would have the Pyro sample statement that you have up here defines basically the global variable. And then conditioned on those, you have that the Pyro plate statement here specifies the local variables here to be conditionally independent given the global context variable that you're in, if that's what you're hinting at. So are you referring to the deseparation rules that Celia talked about? That so here we have a diverging connection up here. So these local components that you have here would be conditionally independent given the global variable that you have on top. If that makes, not quite? That was not what you were referring to? Okay, that's fine.
May I also ask one straight question?
Yeah.
I understand how it plays with the
Yes, so the first argument you have here, even though that it may look a bit, this is just the name of the plate that you can access afterwards. This part here indexes the observation that you have up here, so the dictionary. So this here will just be a tensor that you get. And then we are taking the shape of that, and that would be the number of elements that you have in your tensor. So here, pyro plate is just being informed that the number of components that you have in the plate here will be equal to the number of observations that you have in your sensor.
If I have more than one dimension, then this sort of refers to the last one, for example, or something like that?
That would depend on what you are iterating over, so to speak. So if you're defining, now we have 10 days or 10 places, and this is sort of the number of replicas that you would like to see of your local model. So here you're specifying the number of replicas that you would like to have. So you could have, that does not mean that you cannot have more complicated distributions down here. This is just an indicator of how many times you iterate. You could also have plates embedded within plates. So if you have other types of local conditional independencies, you can encode that via the use of nested plate structures.
Cool. Yeah, I imagine there must be some convention going on, but maybe it's obvious.
So the convention here would be in the direction of the standard syntax or the standard semantics that you have for plates. That you are indexing, you're providing an index to where you're iterating over here, and that's sort of implied down here where you have the observations.
Yeah, and for example, if the singular observation was like three-dimensional, because I have, I don't know, 3 sensors at a time, then there is the question of order of the dimensions, I guess.
Yes, so then you would take sort of the number of observations specified up here, but you would still have access to all 3 dimensions down here. So this is just the index there for iterating over.
Yeah, also worth mentioning that it annotates from the right side. There is another option to mention, div equals -1.
Oh, okay. I guess that was my question. Thank you.
Okay, thank you. Yeah?
Just a clarifying question. So this, with pyro.plate, is actually changing the model and saving it in the dictionary of models under the name of the model. Is that right? So like there's a model called mean.
There is a variable called mean temp in this case here.
And that variable is being changed in that with pyro.plate statement.
No, it's not being changed. Or at least, maybe I don't quite understand what you mean by changed in this case.
For these are observations that are supposed to be conditioning our model. And our model is supposed to be returning like a temperature given a sensor measurement.
Yeah, yes, given these sensor measurements down here, I'm interested in finding what is the posterior distribution of mu-t.
But it will only be doing one at a time. Is that right?
No, it will be handling all of them at the same time. So down here, we are basically unfolding, you can imagine that you're unfolding the plate and simply replicating this local structure here 10 times, and then inserting the observation given in this dictionary here for each of these 10 sensor variables that you have now unfolded. So you, this here, the plate statement here is syntactic sugar, if we disregard the computational speedups, but it's just syntactic sugar for specifying that you replicate this 10 times.
So like if the temperature measurement in the sensor is say like 20 degrees, and then a different time I have another measurement that's different, the sampling will be learning from both of those observations in this block.
Yes.
It's not just independently like acting on each one separately.
No, but within, so when you're saying doing things independently, it is doing part of the computations, exploiting that there are independencies embedded within the model. So in that way, there are stuff being done there under the hood to speed up the computations using the independent statements implied by the model.
Would it work if I move mean temp inside the context?
So the question was, would it work if I moved mean temp inside the context? Do you have an idea what you would get out of it? What would be the implied model by moving it with inside the plate notation here?
So, to my understanding, the important part is to have the final thing, the sensor, this observation inside the context, and the rest is not important whether it would be inside or outside.
So in this case here, we can actually, I think it would work if we directly move it in. So you can see here what it does. So you should never do this, but let's try anyway. So notice here we have mean temp outside the plate, and now we get it inside. So that means that we have, for each of these 10 observations, they have each its own mean temp variable. So all of these days here are now completely independent of each other. They would not even be, they are not conditionally, so the temperature variables for each of these 10 observations are not independent condition on the temperature variable, because you have a temperature variable for each of the data points, the mean temperature variable for each of the data points.
Okay, now it's perfectly clear.
Okay, perfect. Yeah?
Maybe one additional question regarding the syntax. When we use the context manager, data context manager, then we are forced to use the same prior parameter for all the variables in the plate. Is that right?
Now I should be I'm a bit hesitant, because not to say something that's, so you are forced to use the same parameters. So you could basically put, so Pyro is Turing complete. So you can basically put anything that you want within this construct here. So in that way, you could define a bunch of parameters outside your plate and then also refer to it from inside the plate. But so it depends a bit on what you mean in terms of what kind of constraints that you're looking for, what you can and cannot do. And that's...
No, it's okay. I was just wondering, for example, the temperature variable, where we assume variance of 2 across all variables in this aspect, whether it's possible or not to say, for example, I don't know, the more temperature variable has not a variance of 2 but a variance of 4, for example. Whether we can specify this inside this context manager.
That you can do, yes, that you can do. Okay, I think I just need to return this here, otherwise my next illustration won't work. Okay, and we are back to this model here again. And now we do learning, and same thing is actually the same as we've seen many times before. I just wanted to also illustrate here the difference between our maximum likelihood approach and our Bayesian approach. So remember, for our maximum likelihood, we saved the result of the calculation in MLE mean temp. And this is sort of the orange vertical line that you get here. And the blue curve here is our posterior distribution. So again, our posterior distribution maintains the uncertainty that we have, and also illustrates sort of how confident that you can be in the predictions that you have here. So again, just wrapping things up in terms of maximum likelihood estimation and Bayesian estimation, or maybe not wrapping up, but at least illustrating the point again here. Good. We also have several exercises for you, but this is not exercises for now. This is sort of something that you can play around with when you have time after the banquet tonight or another day. But there's stuff to play around with here, and also more complex models that you can maybe find inspiration in if you want to dive further into Pyro. Good. Then in terms of guides, for now, we just use the default guides in Pyro and relied on normal distributions for approximation, so for our variational approximations. So with Pyro, what we're doing is variational inference, and the way that we define our variational distribution is through these guides, or our Q distributions. And they can, by the way, also be used for other stuff within Pyro, so you can use your guides for variational, but you can also use it for importance sampling and MCNT and so forth. So what we're talking about now is a bit more general than just the variational component. So again, Pyro guides, when you specify it, can be arbitrary stochastic functions. And they are designed so that they produce samples from those variables in the model that are not observed. So what it means is that if you have a model specification here, so this was our very simple temperature sensor model from before, where the sensor variable down here is observed. If we want to specify a variational distribution in the form of a Pyro guide for this model here, what we would have is, let's say that we want to specify it as a normal distribution with two variational parameters, one from the mean and one for the standard deviation. We define a sample statement down here, and the sample statement should have the same name. So the variable that you have in your guide here should have a name that matches exactly the name of the variable up here. So we are matching temp here to temp up here. It's defined as a normal distribution with the two variational parameters A and B. And A and B are defined using the Pyro param statement up here, also giving unique names and initialized to certain values. In this case here, we initialize them to 0 and 1 respectively. And then we are also putting in the constraint that B should be positive. So we have the keyword here, constraints, for ensuring that. So the guide needs to have, besides having the same name for the variables that are not observed, so the same, there should be a one-to-one match between the unobserved variables in the model and the variables or the sample statement that appears in the guide. It should also be so that they have the same signature. So if the arguments that goes into the model should also go into the guide, even though the guide may not be using them. So that's just something to remember. But that's sort of the only constraints that we have here. So what you should do now is to try to play around with Pyro in a very small example here, actually the same type of example that we used before lunch, the simple Gaussian model that we've defined up here, a bunch of variables, normally distributed variables, xi being observed. We are unsure about we have the mean and the precision for these variables here being uncertain quantities with certain prior distributions. And we have that implemented in Pyro. We have that here, including the packages to be used. Here we generate 500 data points with the correct mean from a normal distribution with a mean of 5 and a precision of 1. We have here our model specification where we have gamma and mu specified explicitly. These are the parameters that we define prior distribution over. We have our plate construct here for our variables that we observe using the obs keyword down here. And then we have the first part for the guide specification here, which you are supposed to fill in now. Below, we have code for running all this. So this is just a standard stochastic variational inference. And then there's a bit of plotting down here. And the main point would be to implement your own guide just to get a feel for Pyro, and then maybe compare the results that you get here, in particular how the elbow behaves with the results that you had before lunch in this student symbol model that you can find on GitHub. Okay, let's continue again, 25 minutes left. So this here, if you haven't gotten the solution, then Here's at least an attempt. Again, it is not sort of the only solution here, because with the guide and the variational setup, you are free to choose your own variational distribution. So here we have specified 2 sample statements for gamma and for mu, and you can see these 2 parts here related to the precision and to the mean are not related. So it's basically also implies that we are enforcing a mean field factorization of our variational distribution. It need not be so. So you could also have specified a more complicated model down here where you in some way linked these 2 variables together, and then you would sort of have lifted up the mean field assumption. Not something that we have discussed, but just to let you know that that could be an option. And also when you look at the solution here, when we upload it, release it later tonight, you can also compare it with your own solution. And then if there are differences here, that does not necessarily mean that it's a mistake what you've done. For doing the learning, what you end up with here is an elbow that behaves like this. And the main point here for showing this was just that when you compare that to the results that we saw before lunch, where we did the coordinate variational inference, coordinate ascent, we had sort of a smooth increase in the elbow function here without any of these drops. So the debunking functionality that we said was provided by elbow related to the coordinate variational inference setup. In this case here, where we are doing gradient ascent, we are not given the same guarantee. So you can see sort of these dips here that Helge also talked about. So for the last part here before the break, I will just introduce or go back to another example that we looked at earlier, namely our rocketness dataset, terrain rocketness dataset, and try to model that using Pyro. So now it becomes a bit more sophisticated, and we'll see some other functionality that's provided by Pyro. So the first part here is identical to what I showed you before. So I won't spend too much time on that. So here we are dividing up again the data set into predictor variables and response, and it's each of them is defined as dictionaries with 2 keys, one not in African countries and African countries over here. And we have maybe I should just run this. Okay, there are a few warnings here. We'll ignore them and hope for the best. But I guess I allow that. And this is our data set. We have the same boilerplate code for preparing figures, illustrating the data. We do linear regression for comparison. And now we are sort of, again, using PyTorch, again, which Pyro is based on. So much of this is now somewhat familiar to you with these constructs here. Our regression line, we are training it using least squares. And we learn our model, and we can plot it. So everything is just as we saw before lunch. And then we also have information about slope. Here we have our Bayesian linear regression model. And now we have expanded a bit on that compared to what we had before lunch, because before lunch we focused on this lower part here of the model where we had the bias and the incline specified as uncertain quantities with prior distributions. But we had theta, the precision up here, fixed. So now we're also going to specify that as an uncertain quantity. It's given by a gamma distribution with a shape and a rate parameter of 1 and 1 respectively. And the other guys here is the same as before. We have normal distribution, as you can see here. Again, we have the number of data dimensions. M up here is still just 1. The model here is specified a bit more generally than is called for in this particular example, but here we have M equals 1. And for defining the model in Pyro, so maybe we can just, so we up here have the prior distributions defined over the parameter, the slope, the bias, and theta. So that was the slope that we have here embedded within the W vector, the bias and theta. Again, normal distribution except for theta that's given a gamma distribution. We have that defined here. Theta is a gamma distribution with a 1-1 shape and rate parameter, and then normal distributions up here. Then, because we want to do a bit of analysis of the model later on, we are going to define a deterministic variable here called the predictive mean. And that's just the bias plus our data times the slope that we define here as the mean, and then save it in this deterministic variable predictive mean. And then we have our observations that we are embedding within a pyro plate statement. So we have our response variable is normally distributed with a location, so corresponding to our deterministic mean that we calculate here, and then the scale, the square root over 1 over the precision. And then we have all these guys here observed, and this is what we have, or with the keyword observed. And our model now looks something like this. The deterministic model deterministic node out here stands out a bit because it has sort of plays another role in pyro, and it's not directly connected to Y here, but that's visible in the model specification. For doing guides, we can either do auto guide, as we did before, or we could define our own guide, and this is what I've done here. So we have the, for the bias term, Q, again, indicating we're talking about a variational distribution, variational parameter. So B, location and scale, we assume these for the bias and the slope that they are normally distributed with unknown parameters that we want to learn. The scale needs to be positive, so we have that set to introduce the constraint that it should be positive here. We have a theta down here defined as a gamma distribution again, so we are taking the variational posterior to match distribution-wise the prior distribution with two hyperparameters here that is also assumed to be positive, and they are initialized to 1 each of them. For doing inference, we are just having a training method here that takes the data that we're interested in. The guide can be optional. If we don't specify a guide, we just rely on auto guide as we did before. Otherwise, we are using the supplied guide, 1,500 iterations, and optimizing with respect to the elbow. And if we do that, we get some results here. And again, we are learning first we are having a for loop out here, where we are iterating over African and non-African countries, and we're optimizing these two data sets independently of each other. So you can see here we have the first 1,500 iterations here, and then the next 1,500 iterations. So we can see, and here we are specifying the loss, so this here should be a negative sign, so that we are actually increasing this here is the negative elbow that we have here. And we can get the results out here by looking at the parameters, accessing the parameter store, parameter keys. And these are the results that we find. So we have, again, a model, a variational distribution for both the non-African and African countries, and we can access all the different values as we have up here. For doing model evaluation, we can look at the posterior predictive distribution. And here, Pyro also has some support for that, and that is using this statement here, Pyro infer predictive, where we can specify our model, we can specify the guide that we are interested in here, that we are using, and then the number of samples. So when Pyro is making these posterior predictive distributions, it's sampling from the posterior distribution over the variational parameters and calculating all the predictive quantities of interest based on these samples. And here we are just setting that we are using 1,000 samples. So as a starting point, we are making the first plot here disregarding all the uncertainties. So we are just taking the predictive mean. So here I am calculating the Y predictive mean I am accessing. So we had here samples predictive mean. That was my, if you recall from my model up here, I had my deterministic function here, predictive mean, defined here, and this is the one that I'm accessing now. And if I am taking the samples over that, or taking all my samples, calculating predictive mean, and then in taking the mean over those, so that will give me a line for the non-African countries and for the African countries, so basically corresponding to standard linear regression, what we have here. If you also take the uncertainty into over the bias and the slope into account, so now we are calculating again we are sampling and calculating the predictive mean, and we can calculate both the mean value of that and the standard deviation, and then plot here the mean value plus minus 2 times the standard deviation to capture 90% of the credibility interval. And we then get these plots here. So it's sort of a bit the same thing that we've shown you previously, where we are sampling different regression lines and then plotting it multiple times. So now we are just showing you the entire region here, the 95% credibility and so on. And if we also take the uncertainty in the response variable into account, so this is what we have here. So now we are looking so up here I was looking at the predictive mean. Now I'm actually looking at the response variable down here. So I'm accessing y here, but calculating the samples again and illustrating both the mean and the standard deviation. And these are then the results that we get here. It's a more jagged because we also have the uncertainty in the response variable that we're taking into account and illustrated here. But you have sort of, before lunch, we saw you some similar plots here that we have done manually with the coordinate variational inference, and there we sort of had the same shapes here. It was just to illustrate that we can get the same thing from Pyro, that's directly supported within Pyro. And lastly, we can look at the distributions that we have here. So here we have the posterior variational distributions over the, for instance, over the slope versus terrain ruggedness index. So this was a slightly more complex example of using Pyro, where we had put in a bit more effort into specifying guides and illustrating some of the other components that you can use, or methods that you can use within Pyro, these posterior predictive distributions. Are there any questions for this? Or why they have trace in front of it? I actually, there are different elbow functions being optimized that you can choose to optimize. For instance, if you have discrete variables, then there is an elbow enumerate, something along these lines at least, where you are using enumeration methods for specifying the elbow. So making it more manageable for certain types of models. Why we have trace in front of it, I can't recall.
Since we are optimizing the lower bound, and since we are using field approximation, should we expect that the certainty will be underestimated?
Yes. So we should.
In general, it is underestimated, not overestimated.
It's underestimated both in terms of what Helge introduced with the KL diversion, that we're using information projection. So there's sort of inherent underestimation through the objective function that we are focusing on, but there's also a component in the mean field assumption that causes an underestimate or enforces this underestimate of the variance through that part also. So there are different contributing factors to having this underestimate that should be generally expected. And that would be something that, now I mentioned that you could have more complex guides before. That could be something to play around with, where you actually try to make a more complex guide and see what kind of effect it has on the uncertainty estimates that you get. Could you maybe repeat that again? So what happens if we what?
So here we have 50 or 49 African nations in this case. So what happens if, once you've done this process, you end up with a graph where you have more data points like outside of the interval?
So this here is based on both your, well, what happens is basically up to you. But this here is based on both a combination of the data that you have, but also the model specification and the guide specification, your variational distribution. So here one would have to validate, assess whether these confidence bounds here, what you get out of the model here, to what extent that you believe that this is accurate. So here one would maybe rely on additional data sets that you can assess, for instance, log likelihood calculations based on, or whether to better assess whether these uncertainty estimates here are accurate, or whether generally whether the model is well calibrated. The two different. Yes. So So the question was how we got the different confidence intervals. So generally here, when I'm moving down through these plots here, I'm just adding additional sources of uncertainty to the uncertainty estimates that are being displayed. And the first one here, so everything here is also relying on the sampling distribution provided by Pyro through these predictive posterior functionality that's included. So the first one here, I'm just looking at the predictive mean. That was the mean value that I calculated in the model specification. And here I'm, for the red line that goes through, that's just the mean value that I have calculated over all these 100 samples that I'm generating. And then I'm taking plus minus 2 standard deviations around that area and then color coding it here. And that was for the predictive mean. And that's sort of before we add the noise from the response variable. And if we want to add the noise from a response variable, then in the samples that are being generated here, I'm going one step further and then indexing on Y instead of predictive mean, where we have the uncertainty from the response variable. And then I'm basically doing the same thing again, but taking into account plus minus 2 standard deviations, but from the samples from the response variable and not just the predictive mean.
Is it about like aleatoric uncertainty and epistemic first?
If it's
about like epistemic and aleatoric uncertainty?
So this here would be including both epistemic and aleatoric uncertainty, in the sense that we're including both the uncertainty in the parameter estimates and in the uncertainty that you have in the response variable that you've specified.
But that's not the case for the first one?
No, here we only have the uncertainty from the over your parameter estimates. So here we haven't really discussed anything about evaluation techniques. That would be also, it would be specific to the application that you're looking at. So here we are talking about regression, and we are taking it in a probabilistic setting. So depending on what you want to really evaluate your model on, you would probably look at different criteria. So whether it's the log likelihood of the data or the model given the data, or whether you're doing predictions here, that that would be dependent on it. But so Pyro here supplies the framework for specifying the models and doing the inference, and then afterwards there are opportunities then for doing the evaluations or specifying the evaluation techniques. Is Pyro what? It supports both the score function and the reparameterization trick. So the default so the question was what kind of technique Pyro uses for the optimization. So it supports both. The default is reparameterization, but you can also specify that you want to do score function gradient, possibly for models where score function gradient would be more appropriate. For instance, if you have deterministic variables or variables that are,
So it's somehow better?
you know, discrete variables. Sorry?
So here in your example, reparameterization.
That's the reparameterization, yes. Okay. There's only 3 minutes left before the break, and we have another notebook which we won't be which we won't have time for, but is something that you can play around with. So I'll just give you a brief introduction. It's the same data set, but now we are putting it into looking at it from a different perspective. So everything is the same in terms of data, at least. So this is the data set again. But what we are trying to do is to position it within a classification context. So now we want to make predictions about whether a country is from inside or outside Africa based on the ruggedness index and the log GDP. There is a bit of a boilerplate code here for doing plotting of the data. So here we have it's the same data set plotted now with log GDP and ruggedness index, and the color coding indicates what kind of what type of country we are talking about. Here we have a specification of our logistic regression model, and we have a Pyro specification of our model here in terms of standard, where we're just doing standard optimization. We can train it, and we can evaluate it and get a decision boundary that separates somewhat the two classes here. And the question that we've imposed several times now is, how confident can we be in this? And one way to try to express this is through a Bayesian logistic regression approach, where we are positioning it within a Bayesian setting. So we are specifying our bias and our weight parameters here as uncertain quantities with prior distribution, and define it using Pyro. And the exercise that is up for you now, that again you unfortunately have to do in your own time, we will supply solutions later, is to complete the model specification here in terms of specifying the response here, the bias term for or the intercept term, and also the response variable that we have down here. We rely on an auto guide here. If you are adventurous, you can also try to define your own guide. And then there is a code here for doing training and a bit of visualization of the model uncertainty and so forth. But we won't have time for going through this exercise today, but there will be a solution up on GitHub later today, so you can play around with it.